So far all we have written is Newton's equation and Euler equation on the link, right. We have not actually solved the manipulator problem, we have just written the equations on the rigid body. So now where we start from is that we are given q, q dot and q double dot, and the velocity and acceleration of the base link are specified. Okay. And what we do is we take the linear acceleration of the base as p0 minus g0. Okay. So what we say is, this is something which I mentioned in the previous class also, that instead of writing gravity, gravity, gravity on each link, we just accelerate the base upward by amount equal to gravity. So that will create exactly the same effect, whether you are standing static and gravity is pulling you down, or you are accelerating upward in the absence of a gravity field, it creates the same effect. And why? Because of the curious effect that the gravitational mass and the inertial mass is the same. You are aware of it? So the inertial mass comes from F is equal to mass times acceleration, and gravitational mass comes from where? Huh? W? W is equal to mg, yeah. So that plus there is another one also, right? F is equal to capital G into m1 m2 or small m capital M divided by r squared. So it's just one of the biggest coincidences of physics that these two masses turn out to be the same, right? So people are still trying to solve it as to why the two masses are the same, but luckily for us it's same. We'll take it and we'll accelerate the base of the robot instead of writing the g terms on each and every link. So once you do that, first you go calculating the angular velocity of each link, the angular acceleration of every link, then the angular velocity of the origin of coordinate system I, angular acceleration of the origin of the center of mass, and then the angular velocity of the motor shaft. So this we have already seen the formulas, and then successively you just keep doing kinematics and you compute them. Then you come down, and once you have He, which is the end effector forces, right, which is a combination of force and a moment which is applied on the end effector. Okay, this is just a way of writing vectors and moving them as horizontal vectors and vertical vectors. Don't worry about transpose, basically they are vectors. There are three vectors, you write them either like this. So what we want to write is forces and then the moments. So the way it's been written here is that instead of writing this force, you write the transpose first, so it becomes like this. You do the transpose, becomes like this, you put it together here, so you get a long matrix and then you transpose it. That's what has been done here. So just so that you can write it in one line instead of it occupying a lot of space on the screen. So there is nothing great about this. And then you just write the force I as equal to I plus 1 into mass times the acceleration of the center of mass of that link, mass of the ith link and center of link. Similarly, you write the moment equation, which is slightly more complicated because there are too many terms here. And then when you include viscous and friction torques, you can show that the final expression comes down to a term which is compact like this, defined in terms of Fi and mu I. Fi is here, mu I is here. So you can, depending on whether it's a prismatic joint or a revolute joint, you just get corresponding terms. So each of these are vector cross products or dot products or scalar products. So you can write it in MATLAB, you can write it in your programming language of preference. It's no big deal, you can patch it together. Now one of the problems is that you have to write everything in the first system that we are following. We are writing everything in the global frame, which is inconvenient. If it's a local frame, then things don't change and you can just retain the equation, and in every step you can quickly compute the terms. So we know what to do. You just transform everything into frame I, and then by multiplying by rotation matrices Ri and Ri plus 1, this rotation matrix. So if you do that, you can just work out various terms. So if you have omega I minus 1 multiply rotation matrix, if you are interested in a revolute joint, then you have to incorporate the additional term due to omega I, which is the theta dot I z0, and you just can transform similarly accelerations and then the accelerations of the origin of the ith link. So write everything in a single coordinate frame which is fixed with the ith link. And the method is simple. We know that we know enough about rotation matrices, so we just transform everything. Simply rewrite all the terms and you will get new expressions for tau I. Well, first you get fi and mu I, and then new expressions for tau I, which is here. Now in this you have this nice quantities like I bar II, which is constant, and then RII, which is oh, this is wrong, but this is Ri comma Ci in the ith frame. Okay, so the Ci has gone up here. It's supposed to be a subscript. I'll change it. I'll not try to do it right now. I'll just mess up my laptop. And then this term, the rotation axis of the motor shaft, that is also a constant. And then Z0 is 0, 0, 1 t by definition. So if you are following the DH parameter set, so everything is convenient. So if you want to look at this overall summary, you define what is happening in the base, right, and then you define the velocities and acceleration of at the joints. Then you do forward recursion, and doing this using q1, q1 dot and q1 double dot, and then q2, q2 dot, q2 double dot, all the way to qn, qn dot, q double n, and then doing forward recursion, you will calculate either this set of terms: angular velocity of link 1, angular accelerations, angular velocity of the origin of link 1, that of the center of mass, and the angular acceleration of the motor. So after you have calculated all these terms, you do it first link, second link, third link, you calculate all the velocity acceleration terms that you need. Okay. So once you have done it, then using these terms, you start from the last link, and given the forces and the moments acting on the last link and these terms, you do backward recursion, and then you find out what is fnn and mu nn, and then you simply have to take a component along the joint axis, and you will end up with this term, which is the torque on the nth joint. Once you have done this, like I needed fn plus 1 and mu n plus 1 to calculate fn and mu n, I will need these values to calculate f n minus 1, n minus 1 and mu n minus 1, n minus 1, and then I keep marching back until I can calculate the forces on the forces and moment along the first joint. I take a component and I will get the torque on the first joint. So this is the process by which we march overall. So lot of indices, subscripts, superscripts you have to take care of, and then you need to have your basics clear, when to do, how to do a coordinate transformation and the omega cross. So if you have a fixed vector which is rotating, then when you take its derivative, the derivative turns out to be omega cross that fixed vector. It's something which you have known for 3-4 years now. 3 years, 4 years, 3 years. just have to use that and everything else is matrix multiplications. So, no great understanding here. So, we will go back to this two link planar arm. So, there is y0, x0 and z0 coming out, okay, of this system. So, there are two links. So, out here we will have coordinate systems x1, y1, z1, and then we will also have another coordinate system which is x2, y2, z2. In this case we just kept the robot in the vertical plane, right. So, if you take p0 dot minus g0, that will get p0 double dot minus g0, then you will get this vector 0 g0, okay. And the initial angular velocity is, we assume that the frame is otherwise okay. So, just translating upward in the vertical direction with acceleration g, there is no rotation of the frame or angular rotation of the frame. And we, in this case, the case that we analyzed when we did the Euler-Lagrange method, there is no force. We are just trying to find out that given some values of q's and q dots and q double dots at these joints, these two joints, what should be the torques. So, that is the same problem which we are solving for. So, force and moment end of the link is 0. So, F33 is 0, mu33 is 0. So, you can start calculating the position of the center of mass of link 1, the position of the origin of link of the coordinate axis link 1. So, you get these expressions. Now, physically LC1 and LC2 are negative quantities because we are measuring from here to here and then from here to here. So, there are terms like this which are there. So, they go the other way around. So, physically they are negative quantities. Then you have the rotation matrices which are very simple because this is a literally a 2 by 2 case. So, you have Ci minus Si, Si minus Ci. So, you have two rotation matrices. The third one is identity matrix because you are sitting on that link. And then in this case the two rotors, they are sitting on the joint axis, okay. So, that is again simplifies things. So, Z mi I minus 1 is equal to Z0 and that is 0 0 1 t for I is equal to 1 comma 2, okay. So, they are sitting right at the motor axis, that is very convenient. So, this is the point which I was trying to make, that this is very often the case that Z0 is 0 0 1 transpose. So, what people like Professor Saha do is they realize that okay, this is what is happening. So, then they simplify. So, I have written still large matrices, but all of them do not need to be computed. So, what I am asking you to do in this course is that you write 0 0 1 transpose and put it back into the matrices, do the cross multiplication, everything. People like Professor Saha, they explicitly they take care of the fact that it is of the type 0 0 1. So, some calculation will be simplified. So, that is made explicit in the process. So, then you start doing forward recursion on link 1, you find out omega 1 1, which is very simple, omega 1 dot, the acceleration of the origin of the coordinate frame 1, the acceleration of the center of mass of the link 1, and the angular acceleration of the motor shaft 1, which is very simply it is the theta 1 double dot into kr1, which is the ratio. Then you do forward recursion on link 2, your terms keep, these are still simple, which you immediately know that and then you do not have terms like omega cross. Normally you would expect when you are calculating omega 2 dot, you would get a term which is omega 1 cross theta 2 dot. That is not here because theta 2 dot and omega, they are about the same axis, which is the vertical axis, which is the axis coming out of the plane. So, that cross product turns out to be 0. So, this is simplified and then omega 1 dot m1 turns out to be this term. These two terms are more complicated, I mean they are just larger. nothing very complicated about them, they are just larger. So, you can calculate these two. Then you start doing backward recursion. So, do the moment balance, find F22, mu22. Okay. Now, get smart. Okay. You realize that I want to find components which are eventually along the joint axis. Now, all the joint axes are about the z direction. So, it is unwise of me to try and compute these two terms. So, you just do not compute them, do not compute the moment about these two terms, just compute the z term, it is here. Okay. I am not computing the rest because it is not needed. Similarly, you just come back. Now, why do I have these two there twice? I have to fix it. So, you compute tau 2 as this, then you do backward recursion on link 1, you get f1 and then mu 1 and then tau 1. Again, I do not calculate two of these terms. Okay. You can simplify it. So, there are these terms which come around here, you have m1s, m2s. So, if you write it in terms of link 1 and then mass of the motor, and then m1 LC1 is nothing but m1 L1 minus A1, you write it in these kind of terms. And so, idea is that you want to reduce it to the same set of terms which you use for the Euler-Lagrange formulation, and then examine whether you get the same equation that you got for the Euler-Lagrange. Well, physically you should, but please go and verify whether you are getting a formulation which is identical to the Lagrange formulation. Okay. So, that is important. Well, you should expect that you will get back the same formulation. There is nothing very sophisticated about it. So, is the overall process clear? Okay. That is fairly straightforward. And so, coming to the last words on this, the Lagrange formulation is systematic, and you immediately get terms which are fairly consistent and you are familiar with. You can identify inertia matrix, centrifugal and Coriolis forces. This is autocorrect. And then you can identify the vector of gravitational forces. Okay. So, this format is advantageous for control if you are using control. It is also useful for design because you can play around with the terms, and for example, when we looked at the Christoffel symbol and associated things, I explained that you can simplify the dynamics and you can decouple the equations, make them simpler by selectively adjusting terms or making sure that you have the right cross products and things like that. So, all of that can be done better using the Euler-Lagrange formulation. And if you wish to include more complex mechanical effects like flexible link deformation, you can do that very easily because you just need to add a additional potential energy term and additional kinetic energy term, which you can write for the flexible beam, right. How can you write that? You have done that in mechanics, potential energy of a flexible beam pretty easily, and then you just need to crunch it a bit more, and then you can write those equations. And the Newton-Euler formulation is an inherently recursive method that is computationally more efficient. Okay. And more recently, somebody has gone about and has taken the Euler-Lagrange formulation and written a recursive formulation for that. So, that also becomes easy, but that is, I mean, it is almost unrecognizable from the Euler-Lagrange formulation. So, if you look at the method which is followed, you will say that okay, in principle it is Euler-Lagrange equation, but then you do not see any connectivity up and down between these two things. So, is the method reasonably clear as to what we are trying to do? Okay, so I guess once you start solving it, you will get there, and I think this is the last thing which I wanted to teach today.